Hello, my wonderful students. Hey, Dr. Mandis here. Today we're talking about the trends of the periodic table. The periodic table is lying there before you. You got groups going up and down, periods going across. Groups are kind of cool. Everybody gets that? It's a up and down thing. Why is a period called a period? Period is something that, a set of time where something repeats. It's also just an interval. Just get rid of time, just an interval till something repeats. And the properties do repeat at regular intervals. All right. Boron is a lot like aluminum. Why? Because they each have one valence electron in that p valence sublevel. Fluorine, chlorine, bromine, and iodine, they're really similar because they have 5 in the p. So you have these regular patterns of properties that repeat. All right, and then we can get patterns and trends out of it. We want to get trends out of it because it's kind of nice. If you know a compound that, say, fluorine makes, you can kind of get an idea what chlorine or bromide or iodide is going to do based upon fluorine. This is how we create theories and patterns just in chemistry so we can do chemistry. So let's look at just a couple properties and see how they relate to the periodic table. The properties we're going to look at are electronegativity, ionization energy, atomic radius. Alrighty. Electronegativity, ability to attract electrons in a covalent bond. I put the note in there. Of course, noble gases don't really make covalent bonds, so there is no electronegativity for them. It's not about you zero for the electronegativity. It doesn't exist. Okay, if the bond doesn't exist, we can't measure the electronegativity and say it's zero. We can't measure it because it doesn't exist. So they don't have electronegativities. All right, so if you ever look them up and you wonder what's going on there, it's because there are no covalent bonds. For the ionization energy, it's really similar to electronegativity. Electronegativity is the attraction for those electrons in the bond. Where are those bonds? Valence electrons. Okay. First ionization energy is removing just kind of the opposite valence electron, the first one. Well, if it's highly attracted to the nucleus, that's going to be hard to pull off. And if there's no real attraction there, easy to pull off. Kind of like in school when your teacher passes something around the room. If it's something everybody likes and is really cool, it never leaves like the first kid or two. But if it's something that's really lame, it goes flying across the classroom. Everybody just gets rid of it, gets rid of it, gets rid of it. Okay? If there's a high attraction, it's going to take a lot of energy to break it up. Okay, to overcome that attraction. Atomic radius, kind of the same way. Distance nucleus to the valence energy level. If you got a lot of attraction, like a little kid in a teddy bear, if you got a lot of attraction, he's hugging that puppy, pulling it in, and she's never giving that up. Okay, not so much. There's a lot of distance in between. Okay, so distance from the valence energy to the nucleus. So what I'm getting at here is there's something about the attraction. All right, the major driving force for a lot of these trends is just the attraction of each valence electron for the nucleus. All right. That attraction is going to be based on two things. We got shielding of the nucleus and effective nuclear charge. By shielding, I think the best way is to do the analogy, man. Be at a concert venue or in the auditorium or some classroom. Everybody in front of you blocks the front of the room from you. Okay? Everybody behind you doesn't. Okay? People in the same row as you, not so much. Things ahead that are shielding the nucleus, like nuclear shielding, shield the reactors so those things don't get out. They cover the nucleus with electrons so you can't feel that positive charge. Effective nuclear charge is just that, the effective charge leaking out through the electron shielding. Okay, if your reactor's not shielded really well, or maybe you get the dentist and get those x-rays and they don't really put a good lead apron on you, okay, not a lot of shielding, a lot of positive charge is going to flow out of the nucleus. That's what the effective nuclear charge is. How much gets through the shielding? Alrighty. To do that, let's apply these trends two ways. Once across the periods and then down the groups. I could just slap them at you and say, hey, here are the trends, but it kind of it'll stick with you better if you understand why. And that's actually the cool part of it is why. Okay. From lithium to fluorine, let me go back up to the table. From lithium way down here to fluorine over here, buried amongst all my junk over there. All right. Let's go lithium to fluorine. Most students will say that the atomic radius is going to increase because fluorine's bigger. Okay. Go atomic mass of like 19 versus, I don't know, 6 or 7 or 8 or something like that. Yeah, that's a good 8. I was a little nervous. Anyway, but what happens? Let's just look at that valence electron right here, that groovy little red electron and the nucleus. Okay. Well, lithium only has 3 protons in the nucleus. Fluorine has 9. You would think, hey, going to be more traction with the 9. But fluorine has, 2 valence electrons. This is the shielding. These inner electrons that are moving round and round and covering the nucleus. Okay? You're going to say lithium has an effective nuclear charge of 1 positive, fluorine of 7 positive because of the shielding. Okay, you take the 3 protons with 2 electrons circling, the difference is 1 positive. But for fluorine, you got 9 protons, only 2 electrons circling, difference is 7. Each valence electron feels 7 positive because these valence electrons out here are not obscuring the nucleus. They're not shielding the nucleus from our red little dude. Okay, so fluorine's going to have, that red guy should be more attracted to the nucleus, man. Okay, he's feeling a greater charge. And so he's going to feel a greater attraction for that nucleus because the positive, as you go left or right across the periodic table, the attraction is going to increase because the positive nucleus, the positivity of that nucleus keeps increasing, but the shielding stays constant. As we go in a group now we've got lithium and sodium. And so if I go back up to that periodic table, which I don't know if I can, cool. We're going to compare lithium to sodium right below it. We're just going to go down 1 in the group. Okay. Let's see where I am, if I can actually pick the right one. Nope. Now I picked the right one. Okay. Lithium to sodium, we're going down a group. All right. So lithium, 3 positive charge in the center. Sodium's got 11. That's more than fluorine. But sodium has these 1, then 2 layers of shielding where lithium only has 1. So lithium is still going to have an effective nuclear charge of 1 positive. Sodium, though, is going to also be 1 positive because now those 11 protons in the nucleus have 10 shielding electrons. Because of that extra energy level, we create more shielding. So it looks like lithium's 1 valence electron is attracted to basically a 1 positive charge. Sodium's 1 valence electron is attracted to a 1 positive charge. So the negative positive ratio gig is the same for both of them, but lithium's is closer, sodium's is further away. All right, is that going to make a difference? Probably. Lithium's is in the second energy level, sodium's in the third. All right, the attraction is going to increase between each valence as you go up the group. It's going to decrease as you go down. Okay, does that make sense? As you go up the group, it's going to go down. Lithium's going to have a greater attraction. Sodium's going to have a lower attraction. And that's summarized in the next table. Okay? Usually, arrows are always drawn in an increasing direction. So going left or right across a period, the attraction increases to the right. Going up and down a group, the attraction increases up a group. All right, valence going up and down a group, the valence electrons are closer to the nucleus, so there's a greater attraction. Going left or right across the table, the electrons over here feel a more positive nucleus, so there's a greater attraction. How does that relate to our trends? Well, electronegativity is the ability to attract electrons in a covalent bond, so you would think that wherever the attraction is increasing, that's how electronegativity should increase. I would think. First ionization energy is energy needed to remove 1 electron. Talked earlier about how that if that attraction is increasing, you're going to have more energy to remove it. If the attraction is decreasing, it's going to be less energy. Okay, the atomic radius is just like 2 kids in the class. If there's a lot of attraction between them, the distance between them drops. If there's no attraction between them, kind of repulsive effect, the distance grows. Okay, so if we go across a period, we should see electronegativity and ionization energy increasing with the attraction, and the atomic radius is decreasing with the attraction because as the electron gets more attracted to the nucleus, it moves in, so the cloud shrinks as you go across. This is most often the one most difficult for students to grab. The atomic mass is stuck down in the nucleus. The radius that we're really measuring is of the electron cloud. And as the electrons get more attracted to that bigger, more positive nucleus, the cloud shrinks. If we go up and down the groups, we should see the opposite effect again. For atomic radius, same effect for electronegativity, ionization energy. As the attraction increases, the attraction increases, and it's going to get harder to remove the electrons. For the atomic radius, if you think about it, as you go down the groups, it's probably the easiest one to get of all of them. 1 energy level, 2 energy levels, 3 energy levels. It's just the electron cloud is just increasing by leaps and bounds as you go down a group. To summarize it, I like this pictogram. Atomic radius increases down and to the left with those orange arrows. Electronegativity, ionization energy increase up and to the right with those blue arrows. That is a good one if you're a student in a classroom. slap that down in the periodic table when it's given to you. Just draw those arrows on the periodic table and label them, and then you can apply everything that you need to apply. For instance, in these examples, hey, there's my periodic table. Which is more electronegative, K or Cl? Okay, well, K is here. Cl is over there. Okay, they're not exactly in the same row, but hey, Cl is more up and to the right. We're going to increase with electronegativity up and to the right. Cl is up and to the right, so it just makes sense. They're not in the same period. Cool, but they're more up and to the right, and so Cl is more electronegative. Which has a larger atomic radius? Lead or carbon. You got Pb down here, carbon up there. You would think lead, well, it's just bigger. It's going to have more energy levels than carbon, and that's true. Okay, it's same group further down. If you want to apply the trend, what we're saying here is atomic radius increases going down. So that would be carbon up there, Pb down here. If you want to apply the trend up in the previous one, okay, let's just do Na or Cl because they're in the same period. Draw the trend that applies. Na is here, Cl is there. That tells you the order. We could slap phosphorus in the middle. Phosphorus would be more than sodium, less than chlorine. Aluminum would be in the middle between sodium and phosphorus. You can, once you have the trend, just slap the guys there that are on the period, and it tells you basically how they're going to increase. It's just a trend. There may be hiccups along the way, but it's pretty good. Other one is something that's, what if we do things that aren't related at all? You got gold down here. Arsenic is up there. Okay. For the ionization energy, was I'm asking you of here, ionization energy increases up and to the right. Arsenic up here, gold down there. Gotta be arsenic higher on both counts. Okay. Well, those are the trends. You have to memorize the trends. Use the pictogram to help you out, and life will be good. Hope you like it. I'll definitely talk to you later.